This is Unit 3, Topic 8, creating a confidence interval for a population standard deviation. So when we were making confidence intervals for proportions, they followed the normal distribution. When we were making confidence intervals for a population mean, depending on which case we had, we either used the normal, the z distribution, or the t distribution. Well, when we're finding confidence intervals for standard deviation, they follow the chi-square distribution. If you remember, we covered the chi-square distribution a little bit in topic 5. We are going to do a pretty full recap of it, but in general, it had a very skewed to the right shape. So first, it is the normal distribution squared. There's a reason for this. If you want to know the theory behind it, I can point you to probably a website. The bottom axis, because of this, is always going to be positive values. So from 0 to positive infinity is what the bottom axis will have. There is a different distribution for every single degree of freedom, which again is one less than the sample size. But we're always going to be drawing the same picture. It's going to be pretty close to this red one here every time, just for the sake of ease. So it's important to understand, hey, this is a chi-square distribution. It has a skewed right shape, but it's not as important to nitpick as far as what the specific shape would be for that sample size. Lastly, and this is our most important part on this slide, the distribution is not symmetrical, so we cannot add and subtract our margin of error onto the point estimate. We're going to have a slightly different process. So just as a reminder, when you construct a confidence interval for something that follows the chi-square distribution, the point estimate goes in the center based on area in the distribution. So 50% of the distribution will be to the left, and 50% will be to the right of the point estimate. In the middle is going to be the percentage for our confidence level, and then everything that's left over is going to be split in half for each of the tails. The critical values are now chi-square critical values, and there's two different ones. They are no longer symmetrical. So this is probably the most important item on the slide, is that these are not negative and positive versions of each other, because there are no negative versions on the chi-square distribution. So here is the excerpt from this page of the confidence interval reference tables. We're going to find some similarities and some differences. The first is that the point estimate for the population standard deviation is the sample standard deviation. However, this is kind of with a little catch. It's going to be off by a teeny bit. It's slightly biased is what we would say. However, it is still close enough that we're going to be using the sample standard deviation as our best guess for the population standard deviation. Next, our assumptions. We of course have our random assumption, but the population has to be normally distributed. The central limit doesn't apply here. And the reason is because the central limit theorem is only speaking about the sample mean. So we can't use sample size here. It gets very tempting, but you either need to do a Shapiro-Wilk test for normality or be given that the population is normally distributed. What we'll find that's completely new here is our confidence interval is constructed based on a formula where we have the lower number, which is the square root of this stuff, and then the upper number is the square root of this, and the only thing that changes is the left and right critical values, which are actually switched. So this is not a typo. The right critical value is supposed to come first on the left side. The left critical value is supposed to come second on the right side. Again, as we talked about, sample standard deviation follows the chi-square distribution, and then topic 9, we will not be doing this estimate. So I have a few practice examples to get into before we find our first confidence interval. While this is a little bit different than finding a confidence interval for a mean, we do not have two cases like we do for means. So I'm going to first practice using the tables for this example, and so then we'll actually get into one, because the chi-square tables are slightly different. But So example 1, find the chi-square critical value for the given confidence level and sample size. So A, we have a 95% confidence level in a sample size of 25. B, we have a confidence level of 90% in a sample size of 40. And even though these distributions will look very different with these different sample sizes, just for the sake of simplicity, we are going to be drawing this picture every time. So A is going to involve both a picture and using the chi-square tables. So there's a copy of the chi-square tables in topic 8, but it's also in the same file as the t distribution. So if you print this one out again, you'll have a double copy. So we need 2 pieces for the chi-square tables. We need the degrees of freedom, which is 1 less than the sample size, and in this case is going to be 24. So our sample size was 25, we need 1 less than that. And then we also need, and this is the what I highlighted up here, we need the area to the right of that critical value. So what I did is before I scanned this in, I actually just wrote on the top the confidence levels just for ease. But if we're looking at this value right here, to the right of it is 97.5% of the curve. So that's the reason why this 95% confidence level is on top of the 0.95975 value. So the chi-square value for the left critical value is 12.401. So that's the value that goes here. So 0 is going to be right here on this corner. We have 12.401 right here. Point estimate, whatever that is, will go around here, which I think is about half. So on the upper half, we have 2.5% or 0.025 of the area to the right of this upper cutoff right here. So we're going to use 0.025, but this also links to 95%. So the right chi-square critical value is 39.364. So I would take a moment and pause and make sure that you are able to do part B. It is pretty similar, just with a different confidence level and sample size. So that is 18.493 for the left critical value and 43.773 for the right critical value. 39 is not in the chi-square table, so we would need to round down to 30 instead of rounding up to 40. So I know that seems like a kind of wild, but we would want to do that so that we don't kind of lie about how much of a sample size that we have. So this is example 2. The standard deviation for the weights of 25 randomly selected 1-gallon containers of motor oil is 1.79 ounces. The weights come from a population that is normally distributed. How kind? That's an assumption that we won't have to check now. So A says, what is the best point estimate of the standard deviation? B, perform an assumptions check. And C, find a 99% confidence interval for the standard deviation of the weights. So one thing I want to mention about standard deviation is that as regular people, we really don't encounter or feel standard deviation very often. But one example that I do have is that if you and your friend both get a bag of chips out of a vending machine, and your friend has, almost all air in her bag, and you have almost a full bag of chips, that's where you would notice how much the bags deviate from each other. So in general, though, standard deviation is a really big emphasis of things like manufacturing. Not limited to, but it's most popularly a focus in manufacturing. So first, the point estimate for the standard deviation of the weights is going to be 1.79. It's our only guess, but again, they are randomly selected, so we are assuming that it is probably a good guess. Next, both of our assumptions pass because we know our population is normally distributed. We trust that information that we were given. And then it states that the sample was random, so we pass both of our assumptions. Lastly, to find the confidence interval, we are going to apply the formula directly. And so in order to find these left and right critical values, we're going to need to go to the the t-tables, or sorry, the chi-square tables. So I'm going to exit out and open those and do this one along with you. So we are looking to find the chi-square value for the left and right of 99%. So the sample size that I'm going to use is 25, and my degrees of freedom is going to be 24. So I'm going to be looking across this 24 row. So when I'm using this table, I'm going to look to the 24 row, and I'm going to use the left critical value as 9.886, which actually goes on the right side, which I'll explain why in a second. The right critical value is 45.559, which is going to go in the denominator of the left square root. So the reason that these are switched is that if you want to end up with a smaller number on the left side, you need to divide by a larger number here. If you accidentally switch these, which will probably happen pretty frequently, just make sure you switch them at the end in order to make sure you have lower number and then comma higher number. So the rest of these problems are exactly identical. I included 2 more practice problems on the notes as well as the answers for these, so I'm going to leave those up to you. As always, please feel free to email me if you have any questions.